Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm very happy to have Xing as our invited speaker today. Eric is a faculty member from CMU Computer Science Department. And his research basically is actually has worked on very wide spectrum in machine learning, from fundamental machine learning research to computational biology, and to even for the recently he focused on large-scale machine learning.
All right. I want to begin by thanking Danny for inviting me here. I'm very glad to share with you some of my recent work on system and algorithmic foundations for big learning. So it's a fancy topic, but hopefully you don't get too disappointed after just seeing the topic. So, so I've been working on distributed systems and large-scale learning only very recently. And honestly, this is almost out of a selfish reason, because in my group, I've been spending many years developing different machine learning models for many specific applications, to the point that I was embarrassed that I myself couldn't scale up my algorithms. Especially when I did my sabbatical in Facebook for a year, I failed to deliver my promise to boost their revenue by a certain percentage. So I went home and decided I should really catch up on this line of research. So this is a big project, supported, joined by many of my colleagues and students, which I'm going to show you their pictures at the end of the talk. So here is an opening statement. So, everybody is talking about large data, and what do we want to get out of from large data, right? So in many contexts, people want to make good predictions based on large data. And sometimes one can argue, well, if your goal is to only do prediction, you may not need fancy models. Some very simple models, such as a regression or maybe a black box model like a deep network, can probably do the job. But in scientific research and in many other domains, people actually want to get information out of data in addition to making predictions. And that's actually a picture reflecting that kind of goal, right? It was a picture almost more than 10 years ago when people sequenced for the first time a human genome. They want to piece together the puzzle in the genome to find out the regulation programs and other biological stories out of it. And I just want to quote this sentence to re-enhance that kind of objective, which is that if you are in a forest and you may not necessarily know a tree is falling unless you see it, because the knowledge, if not to be perceived by person, is just raw data, and you cannot really make use of that. Therefore, I think part of the goal in nowadays big learning is to not only make use of big data for delivering certain specific goal, but also to look into the data and find out additional information out of it. And for that, I personally felt that machine learning is a promising tool to provide that kind of capability. And ideally, we want the machine learning to behave like that, right? You have an automatic system, which can consume any sort of data in large quantity, and at the end of the day, you can spin out predictions, hypotheses, and all that kind of thing. But unfortunately, I don't think this very rosy view is happening at this point, for many reasons. And personally, I ran into the following problems, right? First of all, everybody's talking about the same problem. We have too large amount of data, to the point that we really don't have an effective system to deal with this data, especially when we want to use some fancy, analytical tools. And personally, I'm very interested in, looking into what is inside the Facebook network. But the network is very big. Nowadays, it has about 1 billion nodes, and plus all the other meta informations and other, semantic informations in the network. And that creates a big computational challenge. And that challenge is well known. Many people are talking about data being so big, and we need to have big storage system, big computing system to deal with that. But recently, people also start to realize another challenge, which is this so-called big model problem. Right? I put here a model that is known to everyone here. This very big, deep neural network are now really providing a very generic and powerful capability to understand a lot of complicated information, especially latent semantic information on data. But the model has to be built very big to make them really powerful. For example, the recent Google Brain network has about 1 billion 1 billion parameters. And that kind of model really cannot be put into the memory of a single machine. Therefore, you also need to deal with some very complex issues of making distributed computing or parallel inference possible. A third challenge, which I also heard recently through a Microsoft-involved workshop at NIPS, is this so-called huge cognitive space or huge task space, where they even want to do classification, simple task classification. What if we want to do it in a very large scale? Say there are 1 million or maybe even 1 billion possible labels in that classification problem on top of a big data set. And that kind of problem is really unheard of to machine learning community many, many years ago, because we are very used to study binary classification using SVM or regression, or maybe a modest multi-way classification. And it turns out that that kind of machinery may not be so effective in solving problems of this scale. So with that, I want to basically inspire my group to hopefully find a good solution that can be used for addressing not only one, but many of these problems. And this is a very, very difficult goal to accomplish, because what we see now are mostly like this picture, right? So we have a lot of hardware development with different fancy machine configurations and hardware. And on top of that, we have a lot of different machine learning models. And typically, the working style is that if a researcher or a group identify a problem and decide to use one model, he's going to build a team and implement a special purpose development or implementation of that model, especially when you want to make it very big. And then you have this one line connecting the system and the model and the problem. And if you have many problems, you probably run into this kind of thing, right? Which is sometimes doable in large companies like here or in Google, but it is a very expensive investment. And it is also basically pushing university researchers out of this game, because with that we cannot afford putting the team like that and spending the money like that to build this kind of solution. So we asked the following question: is there a more elegant, maybe more economical way of addressing the challenge in big data, big model, and big task based on the available hardware system, using a kind of a thin risk style solution, where we have this bottleneck which provide general purpose algorithmic and system blocks, so that you can, with a very modest amount of effort, somehow customize it with specific problems you want to solve. So the talk I'm going to present today is about our initial effort and some results towards this goal. So there are some existing solutions already direct toward this goal. And here I just want to provide a very, very brief context and to show you where we stand in this bigger context. So this is the bigger picture I see so far. In machine learning, many of the machine learning researchers actually are already aware about the big data, big learning challenge. And their solution is typically of this style. They're going to push for smarter algorithmic development, to the point that they develop very, very elegant algorithms which have the correct guarantee on convergence, which can efficiently make use of an ideal parallel system to spread out the computing task into a distributed environment. And then you have all these papers talking about great reduction of computational cost on some well-designed experiment. But if you really read into the paper very carefully, you will see two typical kind of patterns that I found to be very interesting. One is this micro of in the algorithm or in the pseudocode, where they identify a key step, such as an update in the gradient, or maybe a message passing step, which they call to be parallelizable. And then they're going to parallelize it based on not necessarily a real system, very often an imaginary system which incur no communication cost, no asynchronization loss, and other things. And then they will say, if that happens, my algorithm will converge at a very fast speed. And this experiment sometimes is a simulated one. They basically can sequentially simulate a parallel system and show you a very good answer. But if you put the whole thing into a real system, chances are you either need to re-implement the whole thing, or maybe the whole algorithm isn't really working. Right? So that's basically on the algorithmic side. On the system side, there is also a great movement in pushing for parallel and distributed computing, and there the focus is really to try to push up the iteration throughput that you can do as best as you can in pushing the computing into different machines, and with maybe limited communication cost and maybe even no cost, asynchronous algorithm, and then hope for the best. Usually, such paper do not provide a theoretical guarantee on the behavior of the algorithm, but sometimes in the empirical experiment they will show good answers on certain algorithms. So that's pretty much where we stand in the current research paradigm. And there are some limited effort in the middle which show you a system that provides some guarantee or some algorithm which are more seriously on the system's configurations. So that's basically where the current research effort is directing toward. And in my opinion, we don't yet have a good solution that can offer more generic or even universal solution to the large-scale and the big learning challenge that I mentioned above. So here I'm going to present some recent work from my group in collaboration with some friends in developing a new framework for the big learning problems I talked about. And we call the system Petuum for a reason we can discuss offline. But it contains the following building blocks. Right? It has a big machine learning architect, a system architect, which allow data parallelism, model parallelism, and fault tolerance, and many other intricate issues that you have to deal with in running a big distributed system. And then on top of that, we provide a programming model which allow users at different level, researchers, practitioners, or experts, to make use of the parallel design, with a great kind of hopefully a good reward in a reduction of computational cost. And also we have toolboxes and APIs supplying ready-made implementations of major models such as a deep network or a topic model and stuff like that. So what is behind this system is not a monolithic kind of structure in the system architect or a single algorithmic ideas or just a single combination of the two. In fact, we've been trying to make use of a lot of resources at CMU, and in particular in my group, to push on the research on multiple angles. For example, we do actually put a lot of effort in push the algorithm limit, in designing smarter algorithms, good models, and good representations to enable scalability as much as we can, even on a single machine. Then going beyond that, we're going to migrate such development into a real parallel system and actually plunge into the dirty work to actually do some plumbing and make the system more kind of adapted to the kind of algorithm they are supposed to carry. And finally, we actually also have theoreticians in the group showing analysis, demonstrating such development actually may provide you a good guarantee on the consistency and convergence. So there are a lot of tiny kind of pieces of work existing in different places in this whole landscape. But I'm going to organize talk in these three main kind of aspects. One is about how we do big data parallelism, using a example problem that we've been working on doing large network inference. Then I'm going to also talk about how we deal with model parallelism in decomposing big models into different machines. And if I have time, I'm going to talk a little bit about the task parallelism as well. So let me begin with the first one. So the problem really originated from my own terrible experience at Facebook, where I was asked to actually analyze the whole social network that they have in their system. And so here is the problem. There are many ways of doing network analysis, as you know. And in fact, many of the analysis is more of a scientific one. Say, I want to tell a story, say how communicative the network is, and what is the degree characteristic of the network. And that is interesting, but they are not a problem that Facebook should care, right? They actually are caring about more actionable kind of knowledge on network, such as a personal interest inference or a trend prediction, stuff like that. And specifically, this might be a problem they are interested in. How about I want to turn every people into a pie chart in which every slice indicate the probability of he is interested in certain things, or maybe reflecting his certain social activity. For example, this guy can have a multifaceted social traits, such as his profession being a doctor, and he could have a family, and he also have some regular playmates to entertain himself in other time. And this is a typical new way of doing social community inference, in which we don't simply just group every people into one cluster. In fact, we want to estimate a so-called mixed membership of every individual in a social network. And obviously, this is an interesting query because it allows you to make many interesting predictions like this. So the way we begin with that is, let me first talk about the model before I talk about the system, because the model itself can be a very unique one. First of all, if you think about the size of the problem on a network with a billion node, we probably need to start from the very scratch to think about how do we actually formulate the problem in the first place. Because this adjacency matrix that carry the whole network is no longer feasible to be stored or even read through. They have a billion to the power of 2 number of entries.
It's very, very sparse, right?
It's very sparse, but still very many, and many of them are 0. A typical model for this kind of data has to auto-model zeros. We ask, do we need to do that or not, right? So we choose to use a different representation of the feature, which is called the triangular feature, which has a long history in the scientific literature of being more reflective of the behavior of every social individual. And here is how it looks like. Suppose that now we look at every node. Instead of just counting how many 1 or 0 edges it is involved with, we're actually counting how many times it is involved with different types of triangular relationship, such as for this node, it is in one of these full triangle, it is in another full triangle, it is in a half triangle, and so on and so forth. So this is just another way of characterizing social network features in the big network. And it also reflects a mixed membership involvement of every individual in the network. I'm not going to argue how good it is. There are plenty of papers and empirical studies show the benefit of that, but I'm going to focus on the computational issue of solving a model built on this representation. So the model we employ is called a mixed membership triangular model, which is very much like a topic model, but in this case, the topic are sampled for every individual to create or to generate a triangle that 3 people are involved with. Okay, so here every individual have their pie chart, which is a topic vector or mixed membership vector, and then based on who he is going to interact with in the triangle, he's going to instantiate a particular social role. Say he's want to be a professor, this one is also a professor, that one is a student, then 2 professors plus 1 student may like to form a triangle, things like that. So it's a typical probabilistic program, people are aware about, and but in here we have some non-trivial inference problem. The main inference problems are twofold. Here are the data we actually observe, which is the triangular sufficient statistics in the network. But we need to infer for every individual a pie chart, which is the mixed membership vector, and also this matrix, which is the social interaction between different communities or different social roles, if they are put into a triplet. And typically, on the algorithmic side, there are, roughly 2 main lines of, algorithmic direction, right? One is based on, Monte Carlo or Markov chain Monte Carlo, and the other is based on stochastic variational inference. And here I use the topic model as an example to illustrate the typical operation. Basically, in each of these algorithmic prototypes, they basically are going to visit every random variable, every hidden random variable cyclically. And whenever I visit, I'm going to draw a sample based on a conditional distribution defined on the Markov blanket of this node, which basically gives you the conditional probability of this particular hidden variable being, taking a certain configuration or not. So in the MCMC case, I'm going to toss a die and draw a sample in the SVI case, I'm going to compute a deterministic approximation to that posterior probability. But the computation can be very heavy because this whole step has to happen iteratively on every hidden variable and happen in multiple iterations until they converge.
So for this type of directed, top-down models, how scalable can it go?
Yeah, that's what I'm going to show. In fact, in the traditional literature, they are hardly scalable. If you look at a typical MCMC or SVI paper for a network, they can go about a few hundred or a few thousand nodes. And that's exactly why we are interested in addressing this problem. So there are multiple ways of scaling up. If you look at, for example, a paper from, say, David Blythe's group, he is very obsessed with scalable models of LDA, and his approach is to make the algorithm smarter and smarter. Right? For example, you see ideas such as a subsampling, such as a stochastic estimation, and to the point, I think we also contribute some new ideas in parsimonious modeling to reduce the size of the model. So here we have a number of steps actually pushing up the ideas, pushing up the scalability on a single machine in a shared memory environment. If I'm interested, I can go down to the details of each of these algorithmic ideas. But the good thing is that they have been well established in the community, that they lead to convergent and reliable results. And we have some even more new ideas recently to even make this speed up or acceleration even more aggressive by reducing the variance of stochastic updates, by controlling the learning rates automatically, and so on and so forth. So all these ideas actually are quite valuable, and they actually push up the performance quite a lot. For example, in here, I want to show you just by doing a delta subsampling, meaning that I don't need to look at all my 1 billion minus 1 neighborhood in terms of generating a local estimate. I can subsample a neighborhood depending on how much degree I have in my neighborhood. And with a different degree of subsampling, I can actually turn the inference complexity from a quadratic one down to a linear one, and down to a linear one with a very small slope. Okay? And to the point that we can actually deal with a pretty sizable network. In here, it is a network of the Stanford web graph, which has roughly 250,000 nodes. And we can pretty much finish the whole job in 18 hours for 5 social rows. This is academically quite admirable because it's the first time that such a network can be actually even processed under a series Bayesian graphical model. But of course,
so in that case, the node here in the graph corresponds to what kind of entity?
Oh, here is already the visualization of the mixed membership. So this is a 5-dimensional, social simplex. Okay,
so come out from the earlier the model.
What I'm doing here is actually I'm plotting the theta, plotting the pie chart. Okay, every pie chart corresponds to a coordinate, a point in here, which is a 5-dimensional coordinate, and their actually size corresponds to the degree of that node. So here you can have a visualization of the community or the mixed membership community in a bigger social network. You can see probably some absolute communities and some mixed communities in the middle, and so on and so forth. But unless with the stochastic variational inference idea, we can actually further speed it up. And I can have some impressive number here. For example, for that Stanford web network, which is 250,000, we now can actually finish the whole running in about 10 minutes. Okay, that's actually a quite impressive number. But of course, this 10 minutes is for only 5 social rows, which is a little bit unrealistic. 250,000 people have only 5 rows. That's probably too little. So how about increase them to 100 rows? Okay, we actually can do that in 6 hours, which is still quite good. All right, so these are basically
variational method better or Monte Carlo?
Of course, variational method better. So the previous one was a MCMC with data subsampling, and here it is the stochastic variational inference. So up to here, I think we've been really reaching the limit of algorithmic kind of acceleration. We worked very hard in pushing the algorithm to be smarter and smarter, but up to here, we hit a wall. Basically, the network is still bigger than what we can handle, right? So for example, I just show a network of 250,000, but what if I want to handle, say, 100 million, which is still a fraction of the Facebook network? And even more challenging is what if I want the number of rows to be even more reflective? Because for 1 billion people or for even 100 million people, it's easy to imagine they have 10,000 different rows or even more than that. And with a little very, very simple calculation, you can figure out that even the memory needs for storing such information takes a few terabytes of RAM, which is not feasible for a single machine. And if you run any of these algorithms that we used before, it will take a few years to finish the whole thing. So even a scholarly sound and publication-wise very elegant idea really cannot deliver a practical industrial solution that the companies really need. So that actually pushed us into a corner, and therefore we have to now start to think about how to do the dirty part, the parallel inference part. It is actually not quite trivial to scale this algorithm into a parallel setting. So here is why. Suppose we want to do a very direct data distributed sampling. Say just put the data into different client machines and do sample on each client separately. And usually, when we write our code or do our analysis, we will say, okay, we can replace that update step now into a parallel update where I'm going to wait for local inference information to be collected from different machines. But in reality, this step isn't happen in such a nice way because you have all sorts of problems in the machine, in the system, which prevents you from getting all the message back at the same time. Right.
Over here, the t is the data chunk.
The what?
The t variable in the for loop.
No. This is the iteration count. Yeah, I'm actually using an extremely simple programming model, which suggests that this parallelization can happen automatically, no matter how I do it. I'm basically assuming an ideal parallelization. And the whole point is that if you write in this way, all the computational complexity was swept under the rug. You don't see it, but it's actually happened and bother you a lot in the real system.
I see.
Okay.
The basic concept of stochastic algorithm is that you don't really have the iteration concept. Right? It's just a data chunk, it goes forever. So what do you have? That's why I thought that you would be the...
Yeah, okay. Stochastic inference algorithm by nature it will be even harder to parallelize because the whole correctness guarantee is built on a sequential execution of the stochastic updates. Right? Here I want to parallelize. Therefore, here, I haven't really seen tell you what these steps are. You just imagine there is a step that is parallelizable already. And I'm saying even in that simple setting where algorithm is proven parallelizable, you still need to worry about how the parallelization can happen because that step itself can influence your quality.
Bayesian network is a different story than neural network. In neural network, a lot of work is done on this area. You probably know.
Yeah, and you will see. I will have neural network stories later, in fact, in the second part. So, to actually combat this network issue happen over the network, you have to need to set up a barrier, and then you need to cache the results to wait until a synchronization, and that's actually quite non-trivial. So here is a very simple illustration of how serious the problem can be. So as we all know, the network can have a very limited bandwidth, therefore you cannot pass too many messages in a short time. And secondly, all these different machines may perform unevenly because you are not the owner of the whole machine. Other processes are going there. Vibration, temperature, and uniformity and other things can also perform cause heterogeneous performance. And at the end of the day, here is what we actually observed. We found that when running an LDA on a modest cluster, even in an ideal environment where we only run this only program, no other program are running, and we own the whole system, we spent about a good amount of 80% of the time communicating, and the other fraction is for actual computing. That's a big waste, right? And if we allow the program to run that way, the kind of task that I talked about for the billion node network inference is not going to be solved in a short amount of time.
So in that example, is everything converging on a single sort of master machine that correlates all the information?
Yes, you have to, for machine learning algorithms, if you use a prompt server idea or any other ideas, you have to have a collapsing step, right, to gather all the sufficient statistics.
So all that waiting time is on the collapsing
Yeah,
CPU?
yeah,
Okay.
yeah. You have a question there?
Were you using mini batch GPU, or is it that every node just...
Oh, okay. That's another layer of question. Okay, mini batching is a secondary layer of question where, on each particular client, and you compute the update on that other sample over that machine, you can ask whether I do mini batching or I use the whole thing, right? Here I'm abstracting them away. Basically, I'm talking about a generic algorithmic behavior, regardless of you use mini batch or not.
But this timing, it will be affected by
it will be.
Algorithm you use. So I'm asking about here, if you remember what kind of way you mini batching what you do.
I'm not using mini batching in here yet. Using mini batching will be even worse because in mini batching, your iteration, your computing time for each iteration will be reduced, but you need more iterations. In fact, the time spending on the communication can be even worse.
Less on each iteration?
Yeah, so the idea of mini batching is that on every update, I'm going to compute update on a smaller subset of data. Therefore, I actually can compute a gradient even faster, but I need to have more iterations until convergence, right? And more iterations mean actually more time spent on communication, right? So I'm talking about the ideal case. You can actually do a perfect gradient at every step at the a bounded cost, but still your time for communication can be very significant.
Okay. So this applies to the variational learning for graphical model.
It applies to The statement here isn't actually toward a particular algorithm. It's actually a generic algorithm. Yeah.
The basic question is that for variational learning, by default, it's a batch learning. If you look at the mathematical description, I have never heard of anything.
That's a heuristic arrangement. Yeah. If you want to prove a correctness of the variational inferences, you start with a non-batching idea. And if you use batch, you need to further prove it is actually converging, which is not always true, in fact. Okay. Yeah. So here I'm talking always about a convergent, correctly behaving algorithm instead of a heuristic. A heuristic can do anything. For example, you can do the Max Wheeling style parallel LDA, just parallelize it, and they still run. How correct it is, I don't know. Right. So here I want to first make sure it is going to be correct. Okay. Then I will ask the cost of you need to pay, and here is the cost you need to pay. I basically argue that to make things correct, you need to communicate often enough to make sure every update is consistent, and that means you need to have tens of thousands of communications every second, in the parallel distribution process. And this is impossible for a system like Hadoop because that iteration cost is just too high, will totally overwhelm the network. So we ask them, can you actually do something better to reduce the communication or maybe to rebalance the time spent on communication or computing? That's basically comes to the idea about our first part of the talk, which is a better synchronization procedure for parallel computing. So nowadays, there are two major kind of class of synchronization scheme in parallelization computing. One is a bulk synchronous update, right? Synchronization, by the way, is necessary if you care about the correctness of the algorithm. Otherwise, you can just go async. So if you do think, then you need to set up a barrier. And ideally, hopefully, before a barrier, every process will finish about the same time. And then they enter this barrier, get collapsed, and then enter the next update. But this ideal case never happens because of many of the unpredictable unexpected defects in a network system or in a cluster system. What you see actually is here, right? Different process will reach the end at different time point, and then in the collapsing step, I need to do various amount of computing because of this random delay coming from different places. Therefore, a lot of the space which I pointed out here, white one, red one, are actually just the time wasted for computing, for communication. It is not doing any use for computing. And this fraction can be very big to the point that it can take on 80% of the time in even an ideal setting. The other solution to parallelism is to ignore parallelism or to asynchronization. You do totally asynchronous one, and then hopefully in the ideal case, they each different processes will not be off sync by too much. Therefore, you may still get at any point a correct kind of update up to some bounded error. But this is again a very dangerous assumption because in the extreme case, the amount of asynchronism can be very extreme to the point that some threads may be several iterations ahead of others. Therefore, their updates cannot be correctly integrated with other updates. Because what if one gradient tells you to go that way, after a few steps, it asks you to go this way. Then if you average them, which way you go? You cannot get a correct direction. So this is a typical kind of artifacts, nowadays we face in the current parallel computing solution to big learning problem. And we want to actually explore a middle ground where can we actually reduce amount of communication in the BSP, but still get the cost, the speed of async implementation, but the correctness of BSP. That's the question we want to ask. And that leads to the work we presented at NIPS this year, which is called the still asynchronous, still synchronous parallelism, in which we actually set up a timer actually for every process or for every thread, which allow it to monitor how much it is ahead or behind other threads in a parallel environment. And we want to enforce the following update law. First of all, there is a parameter server so that every thread can independently update the parameter server to actually lead to a learning step in the parallel machine learning. But on the other hand, if it needs to go to the next step, it can choose to read the information from the parameter server, which is actually a global solution, or read the information from their local server. Okay, every thread had its local cache of a local version of the parameter state or value. And it reads from the local server if it is not too much ahead away from other processes, meaning that my current version is not much different from the global version, therefore I can read locally. That saves some computation. But if I am too far away from others, then I need to update and read from others, or I need to stop and actually updating myself and wait. So that creates actually a very interesting behavior, which basically allow the slower, for example, this one, threads, to actually do a lot of updates, and without actually reading too often from the global server. But for the very faster ones, it will stop itself at some point, or if it needs to actually update. Every time it updates, it has to read from the global server. Okay, so that kind of balance, you can see this one will spend more time on computing and less time on communication, and that one will spend more time on communication and less time on local computing. And eventually, all these different threads will reach to the goal roughly at the same time point. And here is a rough program interface of the SSP parameter server. Okay, so every machine will have its own connection to this centralized place through a rather simple read and write interface, which is very much it's not much different from a single machine interface, which means that you don't have to rewrite your parallel your program. You can pretty much use the same program convention, and the detailed implementation is taken care of in our low-level infrastructure implementation. And as a result, you can actually see the system did provide a very flexible way of controlling the trade-off between very active synchronizing communication or a more kind of economical stillness synchronization where I don't actually go to the network very often. And the amount of stillness basically specified an amount of iteration cycles that the threads can be deviating from each other. And you can see as the still number comes bigger, the amount of communication actually did go down. And then it gives you a better trade-off between the communication and computing. And this idea can be applied to not just a single model such as LDA. In fact, for a wide variety of machine learning models, such as what I listed here, topic model, matrix factorization, regression, as long as you have a setup where you need to maintain a globally shared parameter to be estimated from the data, and then a large data set, you can always basically distribute the data into different client machines, and then put the parameters into the SFT table, and then do the update in the still asynchronous fashion.
So the data is parallel.
This is a data parallel model at this point. And we assume, of course, the model itself can be stored in this SFT table. Although I haven't really being specific about how this can be implemented. In fact, this one can be also a parallel system, which actually increase the power of its storage. So here I have some performance evidence of this system. We tried a carefully chosen kind of spectrum of different models. LDA stands for atypical probabilistic graphic model inference problem. LDA stands, the lasso stands for a typical, convex optimization type of problem. And here, the matrix factorization is by itself a very popular operation in machine learning. And you can see in each cases, the async, which is actually this one, the still synchronous parallelism, is going to give you the best kind of convergence behavior. And it's not only fast, but also converging to the better actually spot in a given amount of time, faster and more accurate. And people, one thing people asked, care about most is how kind of scalable it is. You can show interesting, curve on a small system. What if I have even a bigger problem that I need more machine? We did an experiment here, which shows that at least, to the limit of having 32 machines with about 300 cores, we still have a pretty nice linear scale up, in which every time you double the machine, you get about 78% scale up, which is a pretty nice, decent behavior in scalability. And lastly, I want to emphasize that this SSE server is not just heuristically divide the data and do distributed update. It actually has a convergence guarantee that the resultant estimate is going to converge to true results if there is one. And the intuition is very, very simple. Because, say taking this stochastic gradient descent as example, ideally, if you don't have any parallelism, you're going to get the accurate gradient. Therefore, you're going to move to the right direction. But now we have the SSP, which basically allow different threads to deviate from each other by certain iteration, and that translates to a small amount of error, due to inconsistency between iterations. But on the other hand, our stillness is bounded. Therefore, the amount of error is also bounded. Therefore, every time you're going to deviate away from the optimal direction a little bit, but they will be a random deviation, and cumulatively, they will still lead to a convergence.
So as you scale the number of machines, the scaleness grows longer for the slow machines, right? And is there some point at which the convergence now goes slower because you've added too many machines and the staleness is too long?
The stillness number is a constant that you can set, which does not have to be dependent on the number of machines.
Really? Because then wouldn't the fraction of network time start adding up to be more than?
No. If you have more machine, the amount of communication will be longer. But the stillness iteration number isn't actually controlling directly the amount of time you need to spend, because I will just check how many iterations I'm away from others, right? So with more machine, I think it is, how should I say, if you have more machines with a constant stillness, you are going to eventually waste more time on communication. Therefore, the effective progress you made will be slower.
So do you know how many machines that is for these typical algorithms?
So here, actually, we have a theorem which actually shows you, a relationship of this. That's actually the beauty of this data analysis. It basically says that your updates, will be converting to the true one, at the rate of this. You have the F and L, which is the typical rate people prove as a function of the data behavior, like the Lipschitz, the smoothness of the Lipschitz constant, and the diameter of the data, and stuff like that. But here we have two other things. S is the number of stillness, and P is the degree of parallelism. Right? So if you have a P, of course, more P, that makes the bound bigger in the lower quality, but you are going to actually get a T there. That if you increase the T, you can smooth, you can erase that kind of effect. Okay. T is the number of iteration. Yeah, iteration. Yeah. And again, the intuition, as I said, is that you have this bounded stillness, which actually allow you to quantify the amount of inconsistency or the error introduced due to these asynchronous updates. And that actually carries through the analysis. Yeah.
If I look at the bound, I would like, okay, I have a certain number of machines, then is that P?
Yeah, it's P.
Then I would set S.
Well, it's a P is the number of threads, so it's
Right,
yeah.
but like let's keep it simple, so it's number of machines. So then I would set S to 0 maybe, right? Then I would get the best convergence rate, right? The smallest upper bound happens when S is the smallest. So why would I ever set, according to this theory, S to any number?
This is a bound. The bigger, the worse.
Yeah. So I want to minimize the bound. So set S to 0.
Well, this bound is more like a qualitative kind of a guidance of the behavior rather than, for example, just as the SVM bound. You don't actually tune the thing to actually give down the bound. It gives you the guarantee that there is a bound exist. But pushing down the bound or up the bound isn't quite meaningful in here because you don't actually know how loose the bound is. There are some other constants in here. Yeah.
Number of iterations, not wall clock time.
Right.
You set S to 0. Your iterations
T is
are
not
going
the
to take
clock
it.
time. It's number
It's
of
not.
iterations. Yeah.
It's number of iterations. So you set S to 0.
Yeah.
Each of those iterations is going to take a while.
Yeah. That-
No,
But
T is
this
just
is a bound on the risk. So can we get a bound? So for example, for equal risk. So right, we have the parameter that we're interested are the risk and the time. Right? We want somehow to tie them together. So how does it translate in terms of if I have K machines and I want this amount of risk I'm willing to take, so I want to converge up to that point. So what would be the best configuration? Does it scale, with the number, the time goes to 0 with the number of machine, or is there some optimal? So how does all these numbers connect?
Well, it does connect in this equation where you keep one thing constant. If you, for example, if you raise the number of machines, you are going to, basically get the bound pushed up in a square of p because more machines, if you don't change the iteration time and don't change the stillness bound, it's going to create more inconsistency. Therefore, your bound is worse. That's the kind of a flavor that you want to get out of this proof.
How does the iteration time change with respect to the number of machines?
Yeah, and S.
And
it's
S.
almost like if you use
It
like an extreme value
is,
distribution or something, maybe you could start to
Right.
come up with some kind of relationship between the two, like for really large collection of machines or something.
Yeah.
right.
So I'm not sure now I answered the question. Like, there are quite a few questions coming to me, so which one should I?
So I think you are talking about just the convergence rates based on number of iterations and number of machines, but you're not talking about the total time spent.
No, I'm not yet.
Right.
Okay, so but
should be more
that is the more important factor.
Yeah, that's to be happening. First of all, this analysis itself is the first of its kind, but it's a typical kind of convention in convergence analysis to worry about iteration. But because the wall clock time is very hard to characterize depending on your configuration, hardware implementation, right? So here we are talking about the more abstract way.
Right, so there is another factor here. So if each gradient computation is very, very fast, and then the communication cost compared to that computation can be very huge. In that case, when you increase the number of machines, you probably don't get a lot, right? Especially if you want to force some stillness.
No, not necessarily. The computation isn't necessarily that fast. For a
GPU cluster, for example.
Yeah, in our case, typically we use smaller mini batch size or using GPU.
Okay,
That's
yeah.
very fast.
That's a different set here. So you are right now already start to suggest a few other ideas that we haven't investigated. Because once you put mini batch, the correctness of this algorithm is not established yet, right? So they become in the heuristic regime. You can do that, but I don't think a analysis can easily be generated.
Or put it that way, if you have a very small task, and if you want to use many machines, what will be the overall time?
A
Will it
small
make
task.
the time increase or actually decrease?
That's a good question. I don't actually have a clear answer at this point. Here, I'm basically on the more pragmatic side. I'm not playing a game. Say, I want to build a big system and run some small task. That's becoming a more kind of a gaming style type of investigation. I'm saying that you really have to do this large computing. You have so much data already available, and this is something you do, and I'm going to guarantee you that it is not terribly going wrong. That's kind of a mentality of this analysis. Okay, so it is by nature not a. Usually the theory, if some of I think some of you may be familiar with that, is to give you the trend, but not the actual kind of reflectance of say you compute the time of convergence. That's never happening, right? So I don't know how to answer because the constant is unknown. I'm just giving you the trend. Yeah.
Right, just speaking empirically, I mean, you've been doing LPA and it looks like maybe up to 32 nodes or something. Have you encountered a point where basically, because it looked like you were still getting some non-trivial speed up when you added the node, like 0.5, 0.6, something like this. Have you encountered situations where essentially it turns over? And I think the sort of spirit of the original question was, hey, it could even get slower. If you had
that's definitely true. That's definitely true. So, for example, I bet you, there is experiment I haven't done. If I do it right now, I could almost predict results. If I put 10,000 machine here, I run the same thing, I'm going to be slower. Okay, that's for sure because there are some other kind of communication complexity that needs to be resolved. For example, the switch isn't big enough to take all messages at the same time. What do? You have to wait. And that kind of constant is not taken in here yet. So here, we still assume, for example, the message are not competing, are not blocking, are not clogging, that kind of thing. But I'm saying that if you have the hardware to support a nice kind of a communication behavior, then this is something we expect. But in real case, I'm sure, you cannot infinitely increase the number of machines.
Actually, we have some analysis on GPU machines, in which case even PCIe cable is not fast enough.
Yeah, GPU is a very, very kind of a special type of configuration, right? It is having a lot of core, but on everything you do the thing very fast. You need to have a big communication. That's why they build together on the thing. If you have a distributed GPU, I'm not even sure whether there are good implementations for distributed GPU yet, because that communication is not easily realizable, across different machines. So I haven't studied that kind of configuration. Right? Here it's more like a classical, traditional, CPU-based clusters configurations. Well, if you bear with me, I have a lot more stories to tell. I want to maybe pass this, but tell the other stories that you may also find interesting. But so even on the serious side, I can have some more results to show that not only the process is converging, but also the variance is also bounded. In a sense, you have a per iteration better quality in the convergence on that. But these are just some add-on qualification. And finally, again, I'm doing this really for real life communication, empirical task. And here I want to show you just a result we achieved by using this system. But otherwise, we cannot be possibly doing that. So on that network, if you remember, we have really social network under the MMTM model. And so we tried to run that on our system and competing with the best system known so far. That's always something we want to try. And here is a network which contains 4 million nodes. That's perhaps the best kind of large network that can be run by any other system. And on this implementation by David Blythe's group, it was done in 24 hours. And in our case, we have 3 hours to finish the whole MSP analysis. And in another network with now 40 million nodes, which is really not very trivial, we can actually finish the computation in 14 hours. And that algorithm isn't deployable because it crashed the machine. Okay, so that's the data parallel part.
So in those cases, were the programs, they have to be rewritten, or were they these like little 2-line changes you were showing earlier?
Their program, you mean, or our program?
Well, the version that you ran on your architecture, did you have to rewrite the algorithm?
Our algorithm or their algorithm?
So if I already have an algorithm, do I need to make any change to use your framework?
Okay, good question. You pretty much don't need to do a lot of change. This is unlike GraphLab or Spark. You need to turn it into a vertex program. We actually are using a native programming, almost like a MATLAB. That's basically at least the goal. So far, I don't know whether your program will be running us, but at least the way we program our model is no different from we program other systems, other than changing the 2 lines of code into this parameter server code. Right? And again, we haven't really built the kind of a full program interface yet, but that's the goal in our system, at least. Okay.
So it kind of feels like you're writing code for one machine.
For one machine? Yeah, exactly. Yes.
Okay.
Yeah. You don't. On your writing of the code, you don't feel a strong kind of low-level parallelism that you have to take care about. Okay. And again, I can just repeat here. The one take-home message is that in this case, the design of the low-level system is not blind of the behavior or the characteristic of the machine learning algorithm itself. We actually are making active use of the machine learning algorithm property, which is the iterative convergence property, so that they can be consistent and resistant to presence of small errors. And that actually is the key spirit in our design, because many of the current distributed computing are putting a lot of emphasis on scalability and sequentialization. That's actually sometimes unnecessary and incur a big cost without too many gain out of it. Okay. All right, so let me move on to the next part, because I'm running out of time, which is about the model parallelism. Again, it is a very familiar problem. Here I have some examples motivating this kind of problem, but you guys have plenty of more such problems in which you really need to do maybe a convex optimization problem in which the size of the parameter is very big. You have, say, billions of parameters. And how to actually make this part effective? In this case, you may have even small data. You can argue, I don't really have a large data problem, but unfortunately, the model is very big. You can still have a need for parallel computing. And here, our approach is, again, divided into 2 kind of different roadmaps. One is about doing the algorithmic kind of innovation to really push for very fast kind of sequential algorithm as much as we can. And again, I think this is not the main focus of this talk, but I just give you some name here for typical convex optimization problems, such as using a kind of a ADMM type of idea to decouple overlapping coupling between different random variables so that they can support to run simple coordinate type of descent algorithm. And for non-convex laws, you can make them smooth and differentiable using a smooth proximal gradient type of approach. And for constraints which are existing in large quantity, you can hierarchically organize those constraints and then do systematic thresholding approach to resolve every consistency and constraint. And again, every of these ideas can push down the algorithm a little bit to make them more and more efficient on a single machine, to the point that you actually reach a bottleneck that your model cannot be stored in a single machine. Then what do you do? So here I want to share with you another idea which is not published yet. It is called the structure-aware parallelization of big models. So how do I draw connection to the existing work? You heard about this shotgun algorithm for lasso. Right? The key idea is that I have a large dimensional regression problem, and I want to make the update parallel across dimension. I'm going to randomly distribute different dimensions into different machines. And then the proof says that if different dimensions are not strongly correlated, I'm going to converge. But if they do correlate, then I don't have any guarantee. The truth is that in many social media and in genetics applications, you almost guarantee to have highly correlated dimensions across different kind of dimensions. Therefore, you don't actually see a shotgun algorithm converge very easily on very high dimensional problems. So this is actually where we want to study our problem. We actually propose an approach which does parallelization based on knowledge of the structure. And also the knowledge of the structure can be a dynamic one because the structure can change during your execution of the optimization. So here's the idea. I'm going to have this system called a STRADS, standing for Structure-Aware Dynamic Scheduler. It is going to constantly examine, any emergent structures, in the high-dimensional space. The structure is defined in a generic way. It could be correlations between different dimensions, could be co-updates across different dimensions, or any other kind of possible behaviors that is kind of tying multiple dimensions together. And then once you discover this
data, the model is just regression.
In this case, it is regression, but it could be also neural network models. It's focusing on the behavior of the coefficients.
Yeah. The data, the raw data.
Yeah. No, it is not raw data. It is a coefficient, which is the estimate of the parameters. So yeah, that's another difference. We don't pre-scan the data and discover structure because that is not possible if you have real big data. We really want to do a bootstrap thing. You come out of nothing. You start to have some estimate. You start to examine whether there are a structure, and you distribute them accordingly. And then you also dissolve any conflict structures in that dynamic thing. Yeah. So as a result, you have this dynamic kind of created clustering of coefficients, and they get distributed into different workers. And within each worker, you have highly correlated one, which should be updated together. And across different workers, you have a decorrelated one. They can be updated in parallel. And such structure will be adjusted either every iteration or every couple of iterations to make sure that you have the best load balance across the whole process. And just to show you a behavior of this on lasso, you can see that even for very high dimensional problem, even for a modest parallelization, a shotgun algorithm is really not quite working well. For example, here we try run shotgun on 2 machines. It is kind of still converging, but slower than our dynamic scheduler. But if you run them on 4 machines, which means a greater deal of parallelization, actually we couldn't observe a convergence. The line just fly away. And this graph is a more kind of hopefully a stronger illustration where we actually simulate the data, okay, so that we actually simulate in such a way that the shotgun algorithm at least can still converge. They are not too strongly correlated, okay? But you can still make use of the correlation structure to hopefully inspire a better distribution of the task to inspire parallelism. And you can see with our STRADS scheduler, once you increase the number of cores to promote greater degree of parallelism, we actually see a very interesting dropping of the convergence, increase of the convergence rate with your increase of the number of cores. And in particular, I found this phenomenon very interesting. If you look at the shotgun curve, or maybe a curve which has a lower degree of parallelism, they are kind of smooth. They seem to have a constant kind of convergence path to follow. But once you increase the amount of parallelism, you actually see that some curves are originally converging at a particular rate, and then suddenly drop down to a different rate and then converge. So why that's happening? I suspect that's happening because you have this dynamic scheduling. You have a distribution, but you are not committal. In the second time, once the structure change, you actually have a redistribution of a task, and then they launch to a different convergence path, which are hopefully even better. Therefore, you can very quickly find the optimal convergence path and then reach to a convergence very rapidly.
So I didn't catch it. So what is redistribute? Which one is
redistribution? Means that you have a million dimension. You put the 10 dimensions in here, another 100 dimension in here, and it's basically you are grouping different dimensions and to allow them to be updated within the machine in a correct fashion, right?
And so what this task of redistributing, that means that you have to actually somehow get these dimensions to the machine, raw data, raw dimension.
Yes.
So how do you handle that?
There is a central scheduler to do task distribution.
If I have a large problem with high dimension, then wouldn't this traffic of getting the dimensions to the nodes will be time-consuming?
Yeah, that's true. But imagine that if you do a shotgun type of random distribution, same thing, because they need to basically also collect information back from every dimension. So this added kind of redistribution isn't a substantial traffic.
But Can you kind of give example to the kind of data set to which you think this kind of strategy can apply?
Oh, in here I'm showing that in Lasso, which basically, it is doing the following. So imagine in every iteration, I have 10 machines, okay, and I have a million dimension. I basically do a planning on a designation of which 10% of the dimension goes to this machine and that machine.
That means that every iteration, I need
you don't have to
set the data, redistribute the data to the different machines.
Yes, and not redistribution of the data in this case.
Parameter.
It is a parameter.
And only potentially if
No,
it's out
but
of
the
data.
data. So I'm missing here something. So
Okay, you are talking about
is dimension 1 million, right? So in order, if I'm a worker and I'm assigned to work on certain coordinates, I need to have the data for these coordinates.
Yes. Good question. Let me tell you a secret. So the truth is that if you look at the Google Brain project, okay, they have a vast, partition of the big network into multiple pieces, and they keep the data multiple copies into different machines. Therefore, they all have the same data. Okay, that's basically the setting in here. Okay, now you ask if my data is really big and I need to do a further kind of partition, then I would say we actually are going to partition the data on that worker machine as well. Therefore, the update will be using only the partial data. So joint data partition and joint data modeling, model partition is one more step beyond this. We actually have a result as well, which I'm going to talk about if I have time. But that requires...
Google's Brain, the one that NIPS 12 paper has both.
No, I think they replicate data. Yeah. If they do both, then it is you can always do a heuristic thing and do both, but you lose the guarantee. The truth is that can you generate or not?
You don't have guarantee anyway.
Actually, the good news is that there are some guarantees even if you do that. We actually proved the new results for that. Yeah.
So in this case, you're talking about with 1 million parameters on 2 machines. That means each machine has about 100,000 parameters.
Something like that.
So every update, every time you're going to check, you have to send 100,000 parameters.
Okay.
Each to the central server, and he has to do this mass comparison to find out the correlation between them?
Okay, very good question. Now we go to details. Remember, this is a sparse regression. And what if you only care about the non-zero ones? Okay, there are actually not too many. Okay, the vast dimension actually is not, it's for you to check, but when you actually want to send the workload, it's not too many, in fact.
But you can compare sparse correlations correctly without having all the, knowing what the zeros are? Or, well, I guess it's, okay, I get it,
yeah, you have the global, the scheduler actually has the whole picture. It has no problem for it to, in fact, what it does is it will subsample, the coefficients and do a comparison of that.
Are these dropouts kind of indicative of when it had to stop redistributing and it sort of found the right?
It is not really. We actually have a plot which I didn't show that gives you a picture about the trade-off between the computing time and the communication time. They're roughly the same as well. Okay, because computing is still quite sufficient. All these are done interleavely. You don't actually need to sequentially wait, right? You actually are doing the discovery of the dynamic structure while the computing is happening, on the client side. So these time are not actually sequential. Yeah.
And then one more question.
Yeah,
when
go ahead.
you do decide you need to redistribute across machines, is it up to the algorithm how they recombine the parameters?
It is not up to the algorithms. The algorithms don't see that. It is inside the scheduler. You can, of course, override the scheduler's default policy and tell it how to distribute. That's actually an API we provide. But the scheduler itself has its own kind of a simplest way of doing that. The simplest way is the shutdown algorithm. Don't do anything, just randomly distribute. Right? That's basically the Graph Labs implementation right now.
Okay.
Yeah. But we just want to sell this concept that the active search of dynamic structure is more beneficial than just randomly distribute, and also it's more correct. Yeah. And this system basically is an implementation that supports that kind of operation, without you do the actual scheduling. Right. Yeah.
How many slides left?
Yeah, I need to run fast. I have about 10 slides.
You have another important meeting.
Let me finish up in about 5 minutes. Okay, and I can skip the third story because that's very simple. So again, without further ado, I'm going to say that just by, hopefully you just believe trust me, that there is a guarantee on also the correctness of this distribution, at least on lasso, for a convergence, which is not actually true for the shotgun algorithm. But here is a kind of very empirical comparison. We did run the experiment on very high dimensional lasso to the point we reached 100 million dimension. And you can see that we compared the shotgun, which is basically the graph lab implementation, with ours. And on like 10 million dimension with a different amount of non-zero inputs, we actually are converging, but a little bit slower, I think, than graph lab. But the truth is that when we get even a bigger dimension, we still converge, and the other algorithms is not even converging for that. And the graph also meant to show you that it is a real scale problem, which is 100 million dimension, which is kind of non-trivial. We also have a very latest result on the preliminary implementation of the DNN. In here, I just want to show that we get the kind of expected scale up of speed by adding more machines because the model is chunked into different sub-machines. Performance-wise, distributed inference is always not as correct as centralized inference, but at least measured from the predictive error, we are not far away from the state-of-the-art deep belief network by Hinton's paper. And this is the same implementation, but on distributed system, and we are not losing much. Mm-hmm.
This is a classic. You are talking about the classification task, right?
Yeah.
But these results are recognition.
Oh no, this is not classification. This is the speech recognition task.
But according to your description, it's the phoneme classification. Are you using hidden mark model?
No, it's not.
You're not using hidden mark model, right?
No, not.
Then it's a classification. So classification task is easier than the recognition task, which the results you quoted are recognition results, I think.
Yeah. Okay, so I got this result last night. It's here. The point isn't to show any other thing. I say that we have the computational speed up in the linear without losing much. That's all I want to show. It's basically saying that this whole strategy is supporting a DNA implementation. We're not trying to invent a DNA algorithm or try to boost performance at this point yet.
Classification could be this one. That's reasonable.
No, typically people don't report classification results. People report.
It's easy to run. The question is who do you collaborate with to run this?
So here it's basically benchmarking, runnability of different models. That's the whole point. I'm not trying to argue this result is ready to deliver and for you to use.
My main question is, are you using stochastic gradient algorithm or not?
I need to check
How
out.
do you this?
It is. I think it is stochastic gradient algorithm.
Okay. So in this case, after each mini batch, do you?
Can we take this? This is a detailed question. Very very high low level. We can take offline and let me deliver the whole message. Yeah. So the insight here again, I'm not trying to say which algorithm and how that model specific. I'm trying to say that there is another dimension in machine learning that you can exploit to build a highly parallel system, which is that there exists a lot of structures in the big model. And if you know how to use that to distribute your task, you usually get a good game out of it. And this claim is not dependent on what algorithm you run or what model you run. Okay. And so this third one, I think I'm going to skip. It tells you how to actually, again, distribute, say, 1 million classification tasks or even higher into a distributed system in a very effective way, which uses some tricky reparameterization of the task space, using output coding idea. But I guess I ran out of time. So let me maybe conclude by the following kind of observations. I think there is a lot of opportunities in doing scalable machine learning if you are willing to do algorithmic development and system development together in the same place, and let them to cross-benefit each other and to cross-inform each other how to write the best parallel algorithm and how to build the best system supporting such algorithm. And in particular, for example, our system made very explicit use of this iterative convergence behavior in which we pay a cost of introducing error, but gain by speeding up the whole iteration to a great deal. And secondly, we discover structures in complex model and then parallelize the components of the model accordingly. And by using these ideas, which is very typical to a wide class of machine learning algorithms, it is very likely for you to get a lot of benefit in distributed computing. And just to wrap up, I want to return to this big picture. I think we are in the process of building this Petuum system, which represents a thin risk connecting the algorithmic needs and the system resource through a kind of generic and universal solution on the system building blocks and the algorithm building blocks. And I think the results are promising. And we are aware about a number of other existing groups making the same effort. And we want to, of course, be in the context. And for that, we also show you maybe a very recent result, just to compare a typical job that people always play in different systems, which is the topic model effort inference, the LDA one. So we ran, for example, the topic model on a pretty substantial data set with 7 billion tokens and with 8 million documents. But we want to make a point that we push the experimental setting out of an ideal scholar or academic kind of environment where you focus your effort on a small number of topics because your memory can hold that many topics. So in here, if you run the whole thing in 100 topics, this red bar is a Petuum, this is a graph lab. The number shows you the throughput in terms of million tokens per second. So we are comparable, although we are about 50% better. But what you really want out of so many number of documents is not about 100 topics. You really want a lot more topics. And people don't do that not because they don't like more topics. It's because if you increase the number of topics, your memory cannot hold the model. In our case, our system can now already support the inference of 10,000 topics. And we reach still a decent throughput in word processing. And the graph lab cannot even load the program because that many topics just blow the whole thing.
Which version of graph lab is this? Is that at CMU time or at Seattle now?
Oh, the current, the most modern version.
Thank you. The whole company people doing this one. So do you have company to compete with them in terms of the evaluation, or is it just a specific example?
What do you mean by company doing that?
Graph lab has the whole company doing it.
Yeah. We just take their tool and implement our graph lab, our LDA on that, right? And we even compared with the Google version of graph lab of LDA. And you can see that we are kind of comparable. At least we can plot the whole thing on the same chart. And but we want to emphasize that here there's a whole team of people building the graph lab in a very specialized fashion. And in our case, it's just a regular implementation on our Petuum system. And we still reach a pretty good speed. And in here again, we didn't compare the larger topic model, because on the 10,000 case, I don't have any result to compare with. So that kind of showcases you the direction we are driving toward for Petuum. It is to support real large-scale, data-intensive and model-heavy kind of inference task, and with a reasonable amount of theoretical analysis, and with a convenient programming interface that people can actually make use of down the road. So with that, I want to close. Sorry for dragging you so long into the talk. And it is an effort involved with many of my students in the group, which I circled here, and also with collaborators who are experts in operating system and the programming language. I think I don't want to read their name anymore, just to save time. But if you're interested, you can email me or talk to me offline to find out more details.